Right now, the space world is certainly buzzing about the most powerful explosion in the universe. A supernova has burst onto the scene in a galaxy quite literally far, far away. Astrophysicist Neil deGrasse Tyson recently made a groundbreaking announcement about our celestial neighbor, Polaris. This shocking and unsettling update reveals that the once stable North Star, widely known for guiding navigators and serving as a steadfast point in the night sky, has undergone a shocking transformation. According to Tyson, recent observations indicate that Polaris has just exploded. The more I look at the universe, the less convinced I am that there is something benevolent going on, sending ripples of incredible cosmic events through our solar system and space at large. In this video, we'll discover the terrifying effects of this startling news that has left the scientific community and stargazers worldwide on edge. How did this fascinating star explode? What effect does this explosion have on Earth? Let's get into it. Astronomers and space enthusiasts worldwide are in shock following Neil deGrasse Tyson's unraveling of the mystery surrounding Polaris's explosion. In a recent announcement, Neil highlights the urgent need for further exploration and observation of this fantastic North Pole star. He also emphasizes the potential consequences of Polaris's explosion, hinting at events that could reshape our understanding of the cosmos. But that's not all, because even after the explosion of this celestial body, something terrifying is said to have emerged. But what is Polaris? What is this terrifying thing, and how is it related to the explosion? Before we reveal that, let's talk about what Polaris is. Polaris, also known as the North Star or Pole Star, is the brightest star in the Ursa Minor constellation, designated Alpha Ursae Minoris, with an apparent magnitude of around 1.98. It's easily visible to the naked eye at night. Its proximity to the North Celestial Pole, less than 1 degree away, establishes it as the current North Pole star, providing stability for navigation in the northern sky. Polaris found a way to make a living in the ocean by gobbling up carbon dioxide and giving off oxygen. They turn the sky blue. Being the closest Cepheid variable, Polaris plays a role in the cosmic distance ladder. According to the revised Hipparcos stellar parallax, Polaris is approximately 323 light-years away, equivalent to 133 parsecs. Compared to Polaris, the Gaia mission estimates a distance of about 448 light-years, equivalent to 137 parsecs. Despite appearing as a single point of light, Polaris is a triple-star system consisting of the primary, a yellow supergiant named Polaris AA, orbiting a smaller companion, Polaris AB. This pair also orbits a third component, Polaris B. Here, William Herschel discovered the outer pair designated AB in August 1779. Were they referring to the AA or AB pair? Polaris AA, an evolved yellow supergiant with a spectral type of F7 Ib and a mass of 5.4 solar masses, is the first classical Cepheid whose mass has been determined from its orbit. But that's not all. It has two smaller companions, which include Polaris B, a 1.39 solar mass F3 main sequence star orbiting at a distance of 2,400 astronomical units, and Polaris AB, or PAR, a closely situated F6 main sequence star with a mass of 1.26 solar masses. Polaris B can be observed with a modest telescope, and William Herschel discovered it in August 1779 using one of the best telescopes of that era. In 1899, W. Campbell reported the variable radial velocity of Polaris AA, suggesting it is a binary system. In 1927, J. A. Moore, recognizing Polaris AA as a known Cepheid variable, demonstrated that the velocity changes along the line of sight were a result of a combination of the 4-day pulsation period, a much more extended orbital period, and a large eccentricity of approximately 0.6. Moore published preliminary orbital elements in 1929, indicating an orbital period of about 29.7 years with an eccentricity of 0.63. This period was later confirmed by proper motion studies performed by B.P. Gerasimovich in 1939 for her doctoral thesis. In 1955, ROA utilized radial velocity data to determine an orbital period of 29.5 years for the Polaris AA system, along with an eccentricity of 0.64. Subsequently, K.W. Camper refined these elements in 1996, establishing a period of 29.5 plus or minus 0.02 years and an eccentricity of 0.608 plus or minus 0.005. A 2019 study by R.I. Anderson provided updated values, suggesting a period of 29.32 plus or minus 0.11 years with an eccentricity of 0.620 plus or minus 0.008. While Polaris C and Polaris D were once considered additional components, further investigation has revealed that they are not physically associated with the Polaris system. Polaris AA, the primary supergiant component, is identified as a low-amplitude population 1 classical Cepheid variable, initially thought to be a Type II Cepheid due to its high galactic latitude. Cepheids, being crucial standard candles for distance determination, make Polaris a subject of extensive study as the closest star of this kind. The variability of Polaris was suspected as early as 1852, and Ejnar-Hertzsprung confirmed this variation in 1911. The brightness range of Polaris is documented as 1.86 to 2.13, but this amplitude has changed over time. Before 1963, the amplitude exceeded 0.1 magnitude, gradually decreasing post-1966, it rapidly diminished to less than 0.05 magnitude, maintaining an erratic variation within that range since then. Reports suggest a recent increase in amplitude, a reversal not observed in other Cepheids. The approximately 4-day period of Polaris has changed over time, steadily increasing by around 4.5 seconds per year, with a brief pause from 1963 to 1965. Initially attributed to secular redward, a lower temperature evolution within the Cepheid instability strip, this change may result from interference between the primary and the first overtone pulsation modes. There is disagreement among authors regarding whether Polaris is a fundamental or first overtone pulsator and if it is crossing the instability strip for the first time. While the temperature variation of Polaris during its pulsations is minimal, the extent of this variation is variable and unpredictable. The erratic temperature changes and the amplitude of temperature fluctuations during each cycle, ranging from less than 50 K to at least 170 K, may be linked to the orbit with Polaris AB. According to Research and Science, Polaris is currently 2.5 times brighter than when observed by TMY, transitioning from third to second magnitude. Astronomer Edward Guinan deems this change remarkable, stating that if they are authentic, these changes are 100 times larger than those predicted by current theories of stellar evolution. But is Neil deGrasse Tyson spot on with his comment? Hold on, because the best part is coming up. Can a star like Polaris explode? If so, how does this happen? A supernova is a brilliant and intense explosion originating from a star, which is Polaris. This phenomenon occurs in the final phases of evolution for a massive star or when a white dwarf undergoes an uncontrolled nuclear fusion reaction. The initial celestial body, the progenitor, may contract into a neutron star or black hole, or be entirely disintegrated, creating a diffuse nebula. The maximum optical brightness of a supernova can rival that of an entire galaxy, gradually diminishing over several weeks or months. The latest supernova directly witnessed in the Milky Way was Kepler's supernova in 1604, following Tycho's supernova in 1572, both visible to the naked eye. Although remnants of more recent supernovae have been discovered, observations of supernovae in distant galaxies suggest an average occurrence of about 3 instances in the Milky Way every century. A supernova within the Milky Way would likely be observable using modern astronomical telescopes. The most recent naked-eye supernova, SN 1987A, resulted from the explosion of a blue supergiant star in the Large Magellanic Cloud, a Milky Way satellite. Theoretical investigations propose that most supernovae are triggered by either the abrupt reignition of nuclear fusion in a white dwarf or the sudden gravitational collapse of the core of a massive star. In the reignition process of a white dwarf, the object's temperature increases sufficiently to initiate runaway nuclear fusion, leading to the complete disruption of the star.